Hello class, and welcome to another set of notes. Hope you all are doing well. This is the we're going to start with the topic 10 theorems. This whole page are theorems from topic 10 that we're going to cover. We are 2 lessons away from being complete, so stick with me. You can do it. Alright, we're going to go down to Theorem 10.10 today. So I'm just going to highlight some stuff. Theorem 10.1, and obviously you get to use your notes. So Theorem 10.1 says if this line here, call it line L, if line L is tangent, then this has to be a right angle. That was from a previous lesson, so we already knew that. The radius and the tangent make a perfect right angle. This was the other theorem from the last lesson. So this says if you take a point on the exterior and you make a tangent and you make another tangent from the same point, these two pieces have to be exactly the same length. Alright? So if this is x, then this is also x. Theorem 10.3, so now a new one. Well, actually, we knew this one too. If, well, no, we didn't. Angle 1 and 2, these are called central angles. Central angles because they have the vertex at the center. And the thing about central angles is if the angles are the same, like if 1 is congruent to 2, then that means that the arcs are the same. If the angles are the same, then the arcs are the same. Those are supposed to be arcs. I can't find that in my computer to do that. Theorem 10.4, kind of similar to Theorem 10.3. It says that if the chords are the same, then the arcs are the same. If the chords are congruent, then the arcs are congruent. Theorem 10.5. This one has a couple things going on. It says, first of all, you need to either have a diameter or a radius. So it's got to go through the center. That's an important part of this theorem. You got to have a segment that goes through the center, so diameter, radius. And you have to have another line that's perpendicular. And if you have that scenario where you have a diameter or radius and a perpendicular chord, then that splits it up like this. This piece here is exactly the same as this piece. This chord here is the same as this chord here. And this chord here would be the same as this chord here. In other words, because of that right angle, you have a line of symmetry. This is a line of symmetry right here because of the right angle. So look for the right angle, you got yourself a line of symmetry in there. Theorem 10.6 says that if the chord is the same as this chord, and it's very similar to Theorem 10.4, which if the chord is the same as the chord, the arc is the same as the arc. This one says that if the chord is the same as the chord, then the length to the middle is the same for both of them. The length to the middle, the distance to the center. And you always measure distance to something at a right angle. That's why there's a right angle symbol in there. Theorem 10.7 is a big one. We learned up here, we've learned in the past that like if this is a 60-degree arc, then this is a 60-degree angle. The central angle is the same as the arc. This is not a central angle. This is called an inscribed angle. So maybe make a note of that. That's an inscribed because the vertex is on the circle like that. If it was in the center, it'd be a central angle. It's called an inscribed angle. Do you think the inscribed angle will have the same measure as the arc? And that is incorrect. In fact, it ends up being that the measure of arc AB is twice as big as this angle. So if this is like a 30-degree angle, then this would be a 60-degree arc. It's going to be used quite a bit. this angle is half of the inscribed arc. This is called it's called the intercepted arc. I'm sorry, intercepted arc, inscribed angle. Theorem 10.8. We've got two inscribed angles. We got angle 1, and angle 1 has this arc, and then we have angle 2, and angle 2 has this arc. So angle 1 and angle 2 have the same arc, which means angle 1 is going to be congruent to angle 2. So if you've got two inscribed angles with the same arc, then they are the same angle. Theorem 10.9, very similar to Theorem 10.7. It says if this is a semicircle, it's 180 degrees, right? So that means that the angle, just like up here, if this is 60 and that's 30, if this is a 180, this will always be a 90 degree angle. So if you see a diameter in there, or you see a semicircle, this will always be a 90 degree angle. And the last theorem of this section, feel free to rewind and re-listen to all these. It says that if you've got a quadrilateral inscribed in a circle, it turns out that this angle here and this angle here add up to 180. So A and C add up to 180, and B and D add up to 180. Alright, so those are all the theorems. Alright, now we're going to do some problems. There's a lot of problems on here to do. We don't have to do all of them. Some of them are quicker than others. Like example 1 is pretty quick. We're going to use Theorem 10.7 here, which says that the angle, the inscribed angle, is half of the arc. So if this inscribed angle is 60, we know that this arc has to be 120, and y is a central angle, so it will be the same. Alright, so 120 for that one and 120 for this arc. It's very similar here. This is 90, y has to be 90, that's a 90 degree arc because this is a 90 degree central angle. And how do you find the inscribed angle? If the central angle is 90, the arc is 90, the inscribed angle will be 45. Alright, 45 degrees for that. Number 3, I see a diameter. And so if you look at Theorem 10.9, in the case of a diameter, you always have a right angle. So that makes this a nice 90 degree angle. So just put 90 for that one. Now this starts to get kind of fun here. These are puzzles. This 30 degree angle is to this angle right here. And we have to use that to figure out, well, actually, you know what? It's really not that hard, because look at this. This is an inscribed angle, and this is the arc. So that, because this is 30, that means this is doubled. That's just 60 degrees. So actually that one wasn't as complicated as it looked. It looked complicated because of all the extra lines, but really it was just one of these. Alright, next problem. This one does get a little bit more complicated. We got a 48 degree angle here, and we've got a diameter, so that's important to notice. So there's lots of ways to do this problem. Here's what I see. I see a 48 degree angle, which makes this arc double. So it's an inscribed angle that makes this arc 96. I see a diameter, which makes 180 degrees right here. So this has to be 84. 96 plus 84 is 180 degrees because of the semicircle. And then lastly, we can say that this arc is twice as big as this angle, so it has to be 42. That was a puzzle. Now there are other ways possibly to get that, but that's just what I saw, and that's how it goes down. Number 6. Interesting. Oh, I see it. I see it. Semicircle right here, which makes this 100, because 100 plus 80 is 180 degrees for a semicircle. And then this arc works with this angle right here. So this arc and this angle are related, so therefore it's just half. The arc is double the angle according to Theorem 10.7. Number 7, in this scenario we're getting in some algebra, and so we're going to start with just figuring out what this arc is. We got 360 degrees all the way around the circle, so I'm going to go ahead and do 360 minus 112 minus 148. Whoops. Redo. 148. You get 100 degrees for that arc, so that makes this arc 100. Just like here, if that's 100 and then that makes that 50. Same thing here, if that's 100, it makes this 50. So for number 7, we're just going to say that 7x minus 6 has to be 50. Alright, because that's what that is. It's half of 100. Add the 6 over, divide the 7, and you get x equals 8. Number 8, same idea. If this is 110, that makes this 70, which makes this angle half of 70. So the equation would be 4x plus 7 equals 35, because 35 is half of 70. So 35 minus 7 is 28. X equals 4 for that one. And then we get into more problems. Again, we're not going to do all of these problems. Number 9 is particularly tricky. We should go over number 9. We have to figure out what this 51x is equal to. And so that's the goal. The goal for number 9 is 51x equals something. Alright, 51x equals something. And here's how we need to do it. We need to use these inscribed angles. So I'm going to take this 98, I'm going to double it. 196. So I know that this whole arc is 196. So now take 120 away from that, and you get 76. This has to be 76. Because 76 plus 120 is 196, and 196 is double 98. Then you got to rework it. I'm going to erase that, and I'm going to use the 89 to do the same thing. What's double 89? $178. Alright, so that makes this whole arc has to be 178. Let's take 76. You get 102 for this piece here. So there it is. 51x is 102. And that works out very nicely to be x equals 2. Alright, number 10. This was back to the previous lesson actually. Because it says assume tangent, what we can do is we can assume that this has to be a right angle, because that's a tangent, it looks like it's a radius, and then you can just do Pythagorean theorem to solve for the length. So real quickly, 6.6 squared plus 8.8 squared, a squared plus b squared equals 121, and the square root of 121 is 11. Alright, so this is 11. That worked out nicely. Skip 11. Number 12. Lots going on here, and this is basically, we're going to start with Theorem 10.5, which we have a nice right angle with some stuff here. So based on Theorem 10.5, because of this right angle, x has to be 5, which makes this arc 10. Sorry, this chord is 10, and this chord is 10. Alright, so these two purple chords are the same length, which brings in Theorem 10.4, which says if the chords are the same, then the arcs will be the same. So that means that if this is an 86-degree arc, this is also an 86-degree arc, and 86 split in half, because this is like the line of symmetry, would be 43 for y. So y is 43. Alright, we can skip 13. I'll give you the gist for 14. 14 is Theorem 10.10, which says in an inscribed quadrilateral, these two add to 180, and these two add to 180. So you're going to have to do a little system of equations there for that one. Alright, number 15. I see the right angle. Because of the right angle, that means that if OM equals ON equals 7, so if these are both 7s, and CM is 6, that means that these lengths are the same as well, because this is the same as that, based off of Theorem 10.6. That's what we could use to say that if this is 6, that makes this 12, which makes this 12. The answer is 12. Okay. Let's skip 16. Let's go down to 17. It says find the perimeter. That's like one of the problems in the previous lesson. This is based off of Theorem 10.2, which says if we've got tangents from the same point, that's the same. So that's 5 and 5, which makes this this piece here has to be 11, which makes this piece also 11, and it makes this piece also 8.5, because 5 plus 11 is 16, by the way. And then you just add all those together. So you get 5 plus 5 is 10, 10 plus 11 is 21, 32, 32 plus 8.5 plus 8.5. Shoot. Oh my goodness. 32 plus 8.5 plus 8.5 is 49. So the perimeter ends up being 49 when you work all that out. Alright. Is AB really tangent? Again, this kind of goes back to the last lesson. If this was truly a tangent, that means that this would be a right angle. Is it? Is it a right angle? Well, let's see here. That's 5 times 3. That's 4 times 3. Is that 3 times 3? No, it's not. If that was 9, it would be a right angle. Alright, so this 5 times 3, 4 times 3, 3 times 3, it should have been 9. It's not. Next, sketch a circle with two... Sorry, I'm running out of time. I'm going to keep going here. Find the length of a chord that is... here we go. This is a good one. Number 20. Find the length of a chord that is a distance of 5 centimeters from the center. So here's our circle. Here's our chord. The chord